Hey, Becomes-ers, this is Mrs. Vanderlei bringing you part 2 of chapter 15, part 4, Blankwalle. And we left off writing out how to make the acid dissociation constant expression for these different weak acids, okay? So we already have done like hydrochloric acid, here's chlorous acid, acetic acid. So now we have hydrocyanic acid, and won't you do the same thing as we've done before? Write out the equation and write out your Ka. The first thing you might want to do is go back and remember what is hydrocyanic acid. So take a brief moment and write this out, okay? All right, welcome back. So hydrocyanic, what is it? My ride has hydraulics. So what is cyanide? Is CN negative, so hydrocyanic acid is HCN. Hopefully you got then this, okay? And there you go. So problem number 8 says, consider these two acids and their KZ, I guess there should be Ka values, okay? So which acid is stronger, HF? Hydrofluoric acid, or what's HClO again? Do you remember what that is? Hypochlorous acid. Okay, so which acid is stronger? In other ways, to think about this, which one's going to ionize more completely? If I word it that way, then maybe it conjures up which one am I going to make more of my products? Which one will make more of the ions is which one's making more products. So maybe that's a clue to you, the one that has the what? The greater or the smaller Ka value. And if you said the greater K value, you are correct, okay? So the constant for HF is greater than the constant for hypochlorous acid. Therefore, HF makes more product than HClO. And again, this is going to mean, scroll up, what's going on here? Well, hang on. So sorry about that. This means that the HF will ionize to a greater extent than the hypochlorous acid, and it's going to make more products. So you have a greater K value. It's going to be stronger. So the one that makes more H plus is going to be the stronger acid. Hopefully that makes sense to you. All right. Well, let's go on. This next page has some definitions. Hopefully they make pretty much sense. A monoprotic, the prefix mono means one. So one protic acid has one proton. So think all of those that have only one H out in front. So as I put some of these up, why don't you make sure you know how to name them, all right? So here's my first one. Hopefully you know how to name HCl. Hydrochloric acid, that's right. So maybe say them in your head, all right? I'll pause a little bit and you can say them in your head. What's HF? If you said hydrofluoric acid, you're right. How about HNO3? Nitric acid, remember I ate something icky. How about this one? If you said chloric acid, you are correct. Well, this one. If you said acetic acid, you are correct. What about this one? You just seen it. If you said hydrocyanic acid, you're right. Let's do one more. How about this one? It's a little bit different. This is nitrite. So what will that one be? Nitrous acid, very good. And then the next one is diprotic, where you have two acidic protons. Something to keep in mind, especially for a later section, is that these are going to come off one at a time. We'll discuss these later, all right? What do I mean by they're going to come off one at a time? So again, let's practice, I'll put them up here and you practice naming them in your head, all right? H2SO4. If you said sulfuric acid, you're right. How about H2SO3? Sulfurous acid, how about H2CO3? Carbonic acid, how about H2CrO4? Chromic acid, here's one you may or may not remember. If you said oxalic acid, you get the gold star, all right? And honestly, there's probably only one good triprotic acid. It would be this one. And what is H3PO4? Phosphoric acid, all right? So we have a couple more to look at. So letter D are your oxyacids, in which the acidic proton is attached to an oxygen atom. And I thought it was very interesting where if you look at the word for our word oxygen in English is actually the German word Sauerstoff. All right, so if you look at that, what does that maybe mean, sour stuff? Well, what do you associate with things being sour? I think of acids, all right? So the early German people who are coming up with a periodic table and they're naming their elements realize that the things that were sour contain this oxygen. They were oxyacids, all right? So if you go back and look at our list, I just again pulled out a few of them. If you were to see the Lewis diagram for all of these, all right, you're going to see the H is actually on the oxygen, not on your central atom. All right, so the all of these, the H's are on the oxygens, not on the central atom. So these are all oxyacids, okay? And then finally, we have things called organic acids. They contain the mildly acidic carboxyl group. That's your C double bond O, OH, all right? Probably the most common one is acetic acid, that is otherwise known as vinegar, all right? There's other ones, but you probably haven't heard of them unless you take organic chemistry, of course, okay? So let's go on. All right, so problem number 9 says describe the differences in equilibrium of strong and weak acids by filling in the chart below. Now, I put in HCl as an example of a strong, so if it works for HCl, it'll work for the other 6. And then all the other acids out there, we've listed some up above, but there's more, a lot more than those, will be what the weak acids will be like. So about the Ka value for a strong acid. So, if it is a Ka value, I said it was huge, right? Remember that? And the 6 strong, the Ka is actually what we call infinity, all right? So what about a weak acid? Does it 100% dissociate? Nope. All right, so the K is going to be less than 1. You're going to have a negative exponent. So the position of equilibrium is to the right because I'm going to have all products and no reactants. And then over here, most of your weak acids, all your weak acids are going to go to the left. You're going to actually end up with more reactants than products, okay? So over here, compare the H at equilibrium to the HA at the original, and they're going to be equal. Why? Because it's 100% dissociated. Whatever the molarity was of the original strong acid will be the molarity of the H+, all right? And then over here, because it just doesn't dissociate very much, it's going to be, oopsie, to the left. Stop that. To the left, you have a Ka less than 1. You're going to end up with more of the original acid still left than the H+, okay? What about the next one? All right, so strength of the conjugate base compared to water. Remember, a very, very, very strong acid will give you a very, very, very weak conjugate base. But a weak acid will give you a stronger conjugate base. So most are going to be stronger than water. Okay, let's go on. So problem 10 says the equilibrium constants of Ka for HCN and HF in water will be 6.2 times 10 to the -10. That's your HCN, your hydrocyanic acid, and your hydrofluoric acid is 7.2 times 10 to the -4th. The relative order of base strength is, so I wrote the stronger the acid, the weaker the base, okay? So you pause this and think about it and see what you end up with. All right, well, let's kind of check this out. So, if I have the strong acids here, all right, what's going to happen next? So the strongest acids will give you the weakest base. All right, so these are the strongest acids. They'll give you the weakest base. So which is my strongest acid here? All right, HF. Yeah, it's pretty strong, 10 to the -4th. HCN, 10 to the -10th, all right? So that's going to be a weaker one. So already the weaker acid will give you the stronger base, okay? So it looks like CN negative is going to give me a stronger base, okay? So the one there's CN is higher than F minus is going to really help you out here. And you know what? The only one of those here is C. Well, what about water, all right? Well, if I have H3O plus, all right, the conjugate base is water. So what does that tell you about this? This is a super duper strong acid. So it's going to have the super duper weakest base. That's why water is at the end. Okay, so let's try problem number 11. Okay, so which of these shows the conjugate bases listed by increasing strength? All right, so in other words, which one here is weakest base in order to the strongest base? Okay, so pause this and think about it. All right, so which is your strongest acid? Looks like the perchloric acid. So this is going to have the weakest base. So right now I can get rid of A, B, and C because D and E have perchloric acid, or the perchlorate as being the weakest base. All right, and then which is your next strongest acid? Looks like HF. Why? Because 10 to the negative 4, F minus. All right, then which is your next weakest acid would be the, this is actually HO acetate. So this is acetic acid abbreviated. And here it is. And then so which is my weakest acid? Right here at 10 to the negative 10 makes my strongest base. So I would say letter E goes from weakest base to strongest base. All right. Let's look at problem number 12 now. Okay. So the conjugate acid of the conjugate base of weak acid is, what do you think? If you said a strong base, you are right. So this concludes section 15.4. I hope this helps. If you have any questions, let me know and we'll talk about them next time. So in the meantime, don't wait to be great. See ya. Bye-bye.